Law of conservation of mechanical energy. First, I would like to introduce an idea of force field. It's not an individual force, point force, it's a field. I think you know this term from, for example, gravity force of some planet or star like Sun. So there is some force field of a sun and it attracts, for example, our Earth to the center of the sun, but Earth is moving on this curvilinear trajectory, so there is also centrifugal force, so it is in equilibrium. Okay, so Earth is moving in a force field of the sun, and and that's all in fact. Only to make some point that it's not so easy, finally, we can notice that because of mass of Earth, it generates also a force field, and there are also other planets which generates force field, so force field might be very complicated. But finally we can say that some force acting on anything depends or is a function of position. So if some point is here, we can calculate the force, resulting force acting to that particle. If some body or particle is here, we can define resulting force to this planet, and so on. So this function is given. Let's say that r is a displacement vector, and differential of this displacement vector is dx, dy, dz. And let's assume that force is given by components fx, fy, fz. So, work of this force W is then integral of scalar multiplication of these two vectors from state 1 to state 2. What is, in fact, if we continue in definite limits, so it's a multiplication of first vector by second vector. What is fx by dx plus fy dy plus fz dz. So because we multiply corresponding components. So now we can stop and we will continue later. Now let me make some notice. Now I would like to define a topic of potential. So let's define a potential. We can denote a potential U, and it depends on position. Similarly, like force. And the part of the definition of potential is that force is equal to gradient of u. And what is the gradient? The gradient is this. It's a partial derivative of u with respect to x. And second component, because it's vector quantity, is du over dy, and last component is du over dz. And total differential of u is du is equal du over dx by dx plus du over dy by dy plus du over dz by dz. And then we talk about u as it is a potential of force field. Potential of force field. And now we can go back. If F is given like this, we can substitute it here. So can you see that? R1, R2 are integral limits. So it is du over dx by dx. We multiply force components with components of differential vector, displacement vector, plus du over dy plus du over dz, and in fact it is du from R1 to R2. So u is a function of r, must be. So after integration it is u at state 1 minus u at state 2 minus u at state 1. In fact it is like this. So let's say some law. If a given force field has a potential, then mechanical work of this force field between two places is equal to a difference of the potential at position 2 and 1. So it's said by words, the same idea what is here. So if force field, this force field has a potential u, then work of this force between two different places, is given by difference of potentials at these places. Okay, so if we know potential, so we can calculate the work much easier by making a difference between these two potentials. So from this follows some conclusion that it doesn't depend on integrational path. In other words, if a force field has a potential and we make a motion from place 1 to place 2, for example in rectilinear motion, then work of force which is needed to displace the particle from place 1 to place 2 is given by a difference of potentials. So here the field has potential U1, and here this force field has a potential U2. So from this follows that it doesn't matter on integration path, it means on path at all. So if I go from 1 to 0.2 in this way, I make the same force, so I need to deploy the same energy as if I go in this way, for example, or if I go by this way or any other way. So it doesn't depend on path, on way. So energy deployed to change the position from place 1 to place 2 doesn't depend on the trajectory, and in all cases it is the same. So it's a feature of such a force field which has potential. So how can we discover that some force field has a potential? For this we have conditions of potentiality. So if partial derivative of fx with respect to y is equal, and there it is changed, fy over x, so its axes are changed, and d if z over dx is equal d if dfx over dz, and dfz over dy is equal dfy over dz. So if these three conditions are fulfilled, then force field has potential. Now let's define potential energy. Let's accept the idea that potential energy V is given by potential U. It's a definition. Somebody figure out this. So we need to accept it now. And how it is given. So potential energy is a negative definition of, I mean negative is a minus here, of potential. So this is a very simple definition. We can substitute it to our previous equation, to this equation of work of force. So it was finally U2 minus U1, and if we use this, so U2 is minus V2 minus V1. So in fact it is V1 minus V2. So then if a force field has potential, if we can define potential energy of this field, then we can calculate work of force by a difference of potential energy. So this is a difference of potential energy. So we also know that V, as it is written here, FDR is equal a difference of kinetic energies. It's from previous lecture. It's a It's a law of change of kinetic energy. Okay, and if we put it together, because this is the same, so we can write that K2 minus K1 is equal V1 minus V2, and we put the values in state 1 together, so it's K1 plus V1 is equal K2 plus V2, and then this law is law of conservation of mechanical energy. It is law of conservation of mechanical energy. And finally, as a last point, we can say that V2 minus V1 is equal minus FdR from R1 to R2. Okay, it's a consequence of what was said previously. So the most important conclusion is that this is a law of conservation of mechanical energy, which says that sum of kinetic energy and potential energy at state 1 is equal to sum of kinetic energy and potential energy at state 2, so that this sum doesn't change.